Okay, guys, get close. Questions while we have a minute? Hopefully we'll finish up the alcohol that we handed out today. Move on to a oxide handout, which I sent by email. Okay, we've done substitution. I think we may be doing finishing up elimination right here. Then we'll move on around. We'll move on to alkylation today. It looks like it's time to go. Okay, guys. Oxidation, we'll skip that for now. We'll move on. I'll send out a handout on oxidation today, most likely. Print out for next week. Okay, let's see where we left off at. Elimination. Dehydration of alcohols to give alkenes. Very common way to make alkene. Very common reaction of alcohols. One for homework. Also, I've been have people over here. We're going to try to get rid of this here and just kind of work with this molding a little bit. Okay, what do we get here? Let's do it like this. Okay, you assess this reaction. I got an alcohol. That's my main functional group. Again, we haven't done any aromatic chemistry yet, so you should just don't do that until we learn how to do this. Okay? Alcohol chemistry. We got an acid. What does this look like? You got to start by saying, okay, this looks like it's going to be what type of reaction? Okay. Reaction of alcohols with acids that do not have a nucleophile associated with them is going to be an E1 elimination to give an alkene typically. So think mechanistically. What can you do here? H3PO4 is a fairly strong acid. It may not be super strong. H+. So all you can do is supply H+, and we can pregnate this, okay? I'm not going to do the full mechanism. Is there any nucleophile? No. No. Sulfate, phosphate, F- will not attack in this class. So what can you do?
Remove the water.
All you can do is ionize. And we ionize, and we get boom, 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 boom. We get this carbocation, loss of water. Now, is there any nucleophile to attack the carbocation? No. At this point, what can happen is this H2PO4 minus can act as a very weak base. Or, I mean, this is an aqueous acid. Or water, your choice. I typically like to use that, although it's not strictly correct. It's strictly correct to use water. You're going to remove an H and put in double bond. What else would you propose to it? What's the other choices?
There's another beta carbon.
Ah, what did you see? What do you?
I mean, like to the right, there's another beta carbon that you could use.
Oh, right. Okay, we could either remove H from that beta carbon or here. Which one would you rather?
The left.
Okay, left. Why? Well, I abbreviated that, but over here is a nice pi system. We can do there. You might skip this step, but is this going to do anything before we eliminate?
No, it's already in the trans. They do want road.
What about this?
Yeah.
Ultimately, this is not going to change the outcome of the product, as you'll see. But is that reasonable?
Yeah.
I mean, that went from what? Secondary? Still secondary, but it's better because now the cation is resin stabilized. Okay, you can do resonance here. What do you call a cation next to a benzene ring? At what position?
Benzoic.
Benzoic. Okay. Now let's eliminate. And if you eliminate, I'll use water. Take the H, these electrons move in. What do you get?
Alkene.
Get the alkene, and it's going to be boom, 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 double bond there. There's your product. Of course, it's going to be trans. Why? Because this thing could rotate to the better like antiform before it eliminates. But we know when you do E1, which product do you get? You get the most stable. Trans is more stable than cis. Okay? So not cis. And of course, you also do not get that product. Now they're both disubstituted. But why is this one better? I reckon resonance works, but I would say because of conjugation. It's basically the same term. But the double bond is conjugated. Isn't a conjugated alkene more stable than a non-conjugated?
Yes.
Yeah, okay. That's a more stable product there. So there you go. I don't know of any other product that you could propose other than E1 mechanism. And then you know your outcome for E1. You always get the most stable with E1. Questions about that? Uh-huh.
With the carbocation,
Yes, Aditi.
with the carbocation, do we rearrange it because that's more stable because it's next to the phenol? Because either way, you
Phenol,
can still
not phenol, phenol.
Sorry. Either way, you can still make it so that the product is formed. It's just like
Right, I could have just taken the H, put double bond in right there.
oh, that's fine.
The only thing I showed you is that rearrangement is not unreasonable. Like I said, you still get the same product if you rearrange or not. Finish it up. What do we get in addition to this? H3O plus and H2PO4 minus. But isn't this how phosphate exists anyway?
Yeah.
I mean, we could have shown this as H3PO4 and water. But how does H3PO4 exist in water? I mean, it exists more like this. So again, I would have probably have shown this taking it. But if you got an aqueous acid, it's fine to use water. Because it's a fast step, what is this first step called? Ionization. This is the fast beta elimination. Because it's fast, base strength is almost unimportant. If you're doing E2, base strength is very important. Because there the beta elimination is in the rate of turning step. Okay, so a lot of review here, yeah? Pocylpyridine. Boom, boom. Actually, do mechanism for this. Primary alcohols. If you try to dehydrate them, minus H2O using sulfuric acid, very unlikely. Why? Because this is E1. Certainly, it's not E2. You can't do E2 with an acid. E2 requires a strong base. And E1 involves carbocation. Are you going to put carbocation here?
No.
No. So it's unlikely that reaction can proceed. A better way to do it with primary alcohols is pocylpyridine. Okay? Let's look at the mechanism. The pocyl reagent is going to be very similar to like thionyl chloride, tosyl chloride. We got a phosphorus double bonded to oxygen and 3 chlorines. The phosphorus does have an expanded octet. But the phosphorus is electron poor because of all these greedy atoms bonded to it. Oxygen acts as a nucleophile here. When we added the phosphorus, what do you want to do?
Add the electron to the oxygen.
Yes, break the pi bond. Now, is this really a pi bond? See, some books just kick the chlorine directly off. Whenever you have a pi bond, for me, never do that. Pi bond up. That's going to give minus 3 chlorines. Oxygen now bonded, the H is there, and the R group is there. The R is the propyl, or I mean pentyl, whatever that is. Do we have charges now?
Yeah.
That's a plus. What's the charge of the phosphorus now?
The same.
It owns one of each bond. It owns 1, 2, 3, 4, 5. It's still neutral. Yeah, it is. Nucleophilic addition. What do you want to do next?
Move this electron down.
Kick off one of the chlorines. Your choice. Phosphorus double bond. Only 2 chlorines left. O, H, R. 1 lone pair, positive charge. What balances this? Cl minus been left. Now see, we really need to draw the R group out. Now we need to do chemistry on the R group. What do we got? A 1, 2, 3, 4. 1, 2, 3, 4. Okay. What are we trying to do? We're trying to get double bond here. All right? We're trying to, we need to beta eliminate. Is this a good leaving group from this carbon? Can you just ionize it off though and make primary carbocation?
No.
No. But let's consider E2 concerted elimination. Pyridine. Pyridine is basic enough to do an E2. Now I could have the base take the H, electrons move in, kick off the leaving group, and that would give a product. I've said this before and we'll say it many times. The problem is the proton. This H is acidic now. It's on positive oxygen, just like H3O+. If this is the base, and acid-base reactions are very quick, like I've said many times, you got to kind of say, hey, this is going to take the H and go neutral. Now, a lot of books won't do this. Doesn't that look like an acidic H? Strictly, this is probably more correct. What does that give? We're going to have the oxygen bonded to the phosphorus, bonded to 2 chlorines. The oxygen now has 2 lone pairs and the pentyl group. Plus pyridine has the H. There's a Cl minus to balance that. It was still over there. At this point, another pyridine, and this has to be a second equivalent. Now we can do an E2. Take electrons, move in, kick off leaving group. And what does this give in terms of the organic product here? It's going to get double bond on the end there, terminal alkene. What mechanism is this right here? E2. There's no carbocation here. Pyridine is strong enough to do the concerted beta elimination. Is this oxygen a decent leaving group?
Yes.
The answer is yes. This, at this point, is very similar to like a tosylate. You know, like the oxygen bonded to the, something like this. Isn't that tosylate? And is a tosylate a good leaving group without being protonated? Okay. It's analogous to that because this oxygen, once it leaves, what do we get? We're going to get a that leaving group, but it's stabilized by resonance. We can draw resonance structures. We also got the chlorines pulling very hard. In the end, it will leave. Analogous to tosylate. Pyridine is strong enough to do an E2. In my mechanism, I'm just requiring 2 equivalents of pyridine. One to take this acidic H, and then one to take this H. We don't call those H's acidic. And another equivalent of protonated pyridine goes with this minus. Okay, so there's an elimination of alcohol by E2, aquapyridine. Questions about that? Is there a lot new there? I don't think there's too much new there, just the new reagent. Similarity to tosyl being a leaving group. Okay, in the end, what does aquapyridine do to an alcohol? It's a way to dehydrate, and it operates by an E2 mechanism. Where you're just plain acid elimination, which operates by an E1 mechanism, that's not good for a primary alcohol. Larry?
With the secondary products here, the pockle, with the negative sign, and the pyridine with the positive charge, would the negative oxygen attack the positive hydrogen?
No, this is pretty stable. I mean, this is going to remain ionized. Just like if you put phosphoric acid in water, it'll probably ionize at least once to that and that. That's definition of a strong acid. The water will keep the proton, right? Well, here the pyridine keeps the proton. And you just end up with a neutralized acid-base reaction. Okay, let's see what we can get down here. Aquapyridine here. Okay, it's an E2 mechanism. We're dehydrating. That right there is enough to be able to have predicted the product. What do we get for that? We know we're doing E2. What does the pocket essentially do? It activates the OH. And the leaving group is actually what? A dichlorophosphate ester. That thing that I drew up there, okay, that's the name of it. That thing will leave. Pocket converts this to that phosphorus thing. Pyridine eliminates. Okay? Are we going to put double bond in the top or bottom?
Bottom.
The bottom is going to be more substituted.
And it's possible.
What's the stereochemical requirement for E2? The H here is trans. So is this? Can this H be eliminated?
Yes.
Yeah. We're going to get double bond here and nothing there. Activate this in your mechanism, then pyridine takes the H, electrons move in, kicks off that activated oxygen. Stereochemical requirement for E2 elimination. The H must be transcoplanar or so-called anticoplanar. Okay, so this is reviewed from organic 1. About the one below. The H down here is not trans. So can you eliminate this and this?
No.
No, but you got two H's up here. Which one's going to be eliminated? Yes. Product here will be, nothing happens down here. And if you wanted to put in the H and label it, it would be HA. Of course, it's no longer bolded because now this carbon is planar. Plane of the board, not forward and back. No change at the bottom, chiral carbon. Okay, so that's aquapyridine. One note here, a couple of you brought this up. Remember we covered thionyl chloride? What does thionyl chloride do to an alcohol? Something for a note card. Reaction thionyl chloride, question mark. Ah, on the back, converts it to an alkyl chloride. Okay? Mechanistic information there. Reviewing. Okay? Your book uses, with thionyl chloride, they use pyridine. You rarely see pyridine used with thionyl chloride if you look in the literature. I don't like to use it in here because when you see pyridine, I want you to think base and I want you to think that E2 elimination. Okay? So I didn't present thionyl chloride with pyridine. With Pockle, I did. Because without the pyridine, you can't do the E2 elimination. Okay, next on our green outline as you come around is what? Same thing that's said right here. Co-alkylation of alcohol, synthesis of ethers. Co-alkylation, that means we're going to put a, what are we going to put on the O? An alkyl. Okay? Terminology is very important to have to understand what's going on. By the way, while I'm thinking about it, y'all checked in the lab yesterday. Where did you put your safety sheets that you signed?
It's on the back.
It's on the back.
Oh, it's on the back now?
Yeah.
Oh, okay. It used to be 2 pages, and I had the bright idea of putting it on the back so it's on 1 page. But I forgot about that. Okay. I didn't look on the back. I was like, where are they at? Williamson ether synthesis. Remember this? Okay. What we're going to do here is the oxygen is not leaving. It's not going anywhere. We're just going to put an alkyl group on it and turn it into an ether. Okay. We're going to do this by an SN2. The oxygen is going to act as a nucleophile. Question though, is this a good nucleophile for SN2?
No.
No. Organic 1, we learned SN2 needs a strong nucleophile, which is typically an anion. What's the only good neutral nucleophile to do? What's the only type of functional group that's good nucleophile in the neutral state? Amines, especially sp3. Neutral alcohol is not a good nucleophile. We stated this in Organic 1 several times. To get this to be a nucleophile, we first have to deprotonate it and make it a minus. Okay? Now there's 2 ways to make it a minus. You could react with a traditional base. Let me show you that first. Sodium hydride. What's the charge of the H? Yes, because sodium is always plus. H minus is called hydride, like chloride. I believe we saw this in Organic 1, right? This will act as a base. These electrons will take the H, leave these behind. What do you get? You get a negative. See, that's just formula. We know that that's ionic, and it's really that, right? Just like if I wrote sodium chloride. We know that it's really plus and minus. And we know that this has 4 lone pairs around it. And so, okay, that is not covalent. This is our O minus. The sodium is just a spectator. What else do we make here? We actually make hydrogen gas. Okay? Hydride is known. I've got some in the lab. That's one way to make the, this is an alcohol. What do you want to call the O minus? That's oxide. This is hydroxide because it's got the hydrogen. What do you want to call something that has an alkyl group? Alkoxide. This is a way to make the alkoxide, the sodium alkoxide in this case. Okay. A more common way to make the alkoxide is not an acid-base reaction, but actually redox. Just react with sodium. And in my lab, didn't we add some sodium to an alcohol? Okay. What did it produce? Remember the bubbles? And then when we added water, it caught on fire. That was the hydrogen that comes out. This is redox. This is just sodium metal, oxidation state of 0. You see, this is not a traditional acid base where we say this takes an H and we make sodium hydride. The oxidation state of sodium is 0. The oxidation state of sodium now is what? +1. Sodium has been oxidized. Now, what's the oxidation state of the H in elemental hydrogen? 0. What's the oxidation state of the H here? It's known to be +1 when it's bonded to it like this. Okay? So the H has essentially been what? Reduced. It's a redox reaction. Redox reactions are usually like radical reactions, and often very hard to show mechanisms for. We know this happens. And this is a much more common way because sodium is very cheap. Sodium hydride is not as cheap. More dangerous. It's harder to store, etc. Okay? So these are two common ways to make alkoxides. Of course, if you want to balance this up here, you can do that because there's only one H over here, but there's 2 over there. So it's not balanced. Okay. So that's the first thing we have to do. Now that we can do that, what's the product here? Step 1. What does this do to the... Okay, is there any change in stereochemistry when we do that?
No.
No, there's not. Then there's a sodium plus that sits with that. I'll be a spectator on it. I'm not going to draw it. Now that we've turned this into a good nucleophile, we add in this. What type of chemistry can take place? I see a halogen, which is typically halogen on an sp3 carbon. What is that?
Leaving group.
Typically a leaving group. This carbon is also next to a p orbital, so it's pretty activated. Remember that transition state? Here we go. These electrons, bam, right there. Kick off the chlorine. What do we get? Boom, boom, boom. Any change in this stereochemistry of this carbon?
No.
No, we did not do backside attack there. We did no chemistry there. Now this oxygen is bonded to that carbon, and that carbon is bonded to what? Obviously a benzene ring. There's your product. I like to highlight the bond we made. Isn't that the bond we just made? By replacing chlorine with our nucleophile, we call that a substitution. What type of product functional group do we have now? Ether. This is called a Williamson ether test.
So if it wasn't a primary carbocation, could it be E1 or it has?
What do you mean carbocation? We didn't make carbocation.
Yeah. I'm talking about in the think of the chlorine in it. So if let's say that was like a secondary, yeah, there. Let's say that like I was like a secondary like carbon. Could you do like SN1 or it's always SN2?
Well, this is a strong nucleophile.
Oh, so you can't.
Remember when I said it was a bully?
Yeah.
This is not going to stand back and let what we ionize. The only time you get ionization is when the nucleophile is too lazy to come in and do backside attack. Okay. Can you do SN2 on a secondary?
Yes.
Yeah, it's not as easy as primary. What about tertiary? Can you do SN2 on tertiary?
No.
No. What if you had a strong base/nucleophile on a tertiary? I'm going to eliminate by E2. Right? I'd recommend pulling out your notes in organic 1. We're doing a lot of just review here. Why are we doing it? Because that chemistry we ended with is very important We're mainly just doing it here in the context, okay, what can you do with alcohols? How do you make ethers? We're kind of focusing a little bit more on the functional groups. Phenols are more acidic than hydroxide. You should know why, okay? Because they're more acidic, you don't have to use sodium hydride or sodium. You can use a weaker, more convenient base like sodium hydroxide. Phenol has a pK about 8 to 10. There's a list in your lab manual of pKa's. Regular alcohol is about what? It's about 16, like water. Okay? It's about 1,000,000 times more acidic because of the resin stabilization of the anion. Here you can use hydroxide, a very convenient, very cheap, readily available base. Take the H, leave this behind. What are you going to get? Of course, there's a sodium here. You're going to get the sodium phenoxide. Phenol. The anion of phenol is called a phenoxide. Did I write that up there? I don't think so. Plus what? Plus water. pK of 16. Let's say this is 10. Which side's favored, 10 or 16?
16.
You see? That side's favored. By how much?
10 to 6.
10 to 6, 1,000,000. Okay? Hydroxide's strong enough to deprotonate phenol. It's not strong enough to deprotonate that up there. Do what? Okay. So predict the product down there. One, hydroxide, what's that going to do? It's going to take the acidic H, the most acidic one. Hopefully you agree that's more acidic than the CHs. It's going to make the phenoxide, turn it into a good nucleophile. We throw this in. See a tosylate, ding, ding, ding. What does this look like? Leaving group. It's on sp3 carbon. See deuterium here. I see some stereochemistry. This is this number classical SN2. We got a good nucleophile. You know, it really doesn't matter. I mean, it's really three-dimensional here. Kick off the top. Do you need to protonate this to make it a good leaving group? No. What do we get? We're going to get that's your O-methyl oxygen. This is now bonded to a carbon here. What else is on this carbon that the oxygen is now bonded to?
Dad. Or no,
No, it's a
yeah,
full
dad is.
vegetarian.
I'm not sure. I'm going to have to look at it to confirm. Not necessarily dashed. It could be bolded depending on how I'm drawing it. But what is definite is this RS? Oxygen 1, carbon 2, D is 3, H in the back is 4. That's S. Since that's S, what is this? This should be R. For this to be R, what do you think is dashed or bolded? Let's put bolded. If it's D, okay, is it really R? O, carbon, D, H in the back. Yeah, that's R. Oh look, it's not dashed, is it? It's bold just like this.
But it's split.
That's because of the way I drew it. If you want to draw it dashed, well then you could draw your product like could draw it like that. Is this R? 1, 2, 3. H is low priority, is forward. Counterclockwise, but since the H is forward, yeah. I don't want to say either. This is the same. In other words, don't fall into the trap that just because this is bold, that's going to be dashed. Depends on how you draw it. It will be inverted. Ultimately, what did we do? Instead of a tosylate, we now have the nucleophile bonded to that carbon. Tosylate was replaced. Okay, when you're doing a Williams and ether synthesis, choice of route is important. Let's do a little synthesis. That is, given a starting material, show how to make this. One of the most common ways to make ethers is an ether synthesis, which involves what? An alkoxide or phenoxide reacting with another fragment that has a leaving group. Can we break this down into that? Let me break it down for you here, and then we can do another example. If I break it here, I can back this up. When you back up, you use sort of a double arrow. It's like I'm going to what would lead to this. So I'm going to back this up to, what's on the end there, a methyl? I'm going to draw it as a methyl. I'm going to back it up to this minus plus this carbon with a leaving group. What's your favorite leaving group, Michael?
Me? Fluorine?
Chlorine? Chlorine is not the best leaving group. I'd maybe go bromine. Is this theoretically, could we theoretically do this now? This is coming forward. Could you envision this kicking off the bromine and an SN2?
No, you don't have to.
This is the A. That is A. Let's do something else. Let's come back. There's another way. What if we cleaved over here? That is, had this alkoxide plus a methyl with a leaving group. Maybe like methyl iodide. Can you envision this oxygen attacking the methyl, kicking off the iodine, and making an O-methyl bond? That would be the B route. And so we would come forward. Here are two options, two potential routes. Which one do you like best? B. Joseph?
B.
Why do you like B better?
Because we did the first one and we did the second one, so we've done the second one.
What's wrong with the first one we did? Again, SN2 because you got a strong nucleotide. Can you do SN2 on a tertiary halide?
No.
You don't do SN2 on tertiary halides, so don't propose this as a good route. Much better route. These electrons attack the methyl. Of course, that's a CH3, okay? Kick off the iodine. Yay, this is a good route. Okay? Choice of the route is important. Down below, show a synthesis of this compound. Which bonds do you want to link together by an SN2 reaction?
You want to cut it to the left?
By the way, this is not actually complete, okay? Because to be complete, you wouldn't start with this. You would start with this here and generate that. How do you want to generate it? Sodium up, okay? So you do need to be able to generate your nucleophile. I'm just showing the already generated nucleophile. That plus how's that look?
No. They have to go.
That's what you carbon contact there. No.
What's wrong with that?
It's not a centrifugal marker.
Marshall, what's wrong with that? You can't do substitution on that carbon. Just because it has a leaving group doesn't mean you can do substitution. Leaving group has to be on the tetrahedral carbon. So don't do that way. Instead, do what? Phenoxide. Plus what? Well, no, we don't need sodium now. We want to make this bond, essentially. We need two carbons. What do we need? Just ethane?
No.
You need a leaving group. You can't displace an H. That's not a leaving group. Iodine, bromine, even chlorine. Tosylate? Yes. How about we just say tosylate? Boom. Pick that guy off. Make the O carbon bond. There you go. Choice of root is important. A couple of questions below for you to think about, including you can also do this chemistry with the analogous sulfur compounds. These are called thiols. Sulfur being under oxygen in the periodic table, very similar chemistry. You'll see a little bit of sulfur in like biochem. Think about why that one's not logical down there. Let's look at reactions of ethers. Okay, I've summed up, finished up alcohols for now. We did 1, 2, and 3. We just did O-alkylation, formation of ethers. We're going to skip oxidation. We're going to move down to chemistry of ethers and epoxides. And the top half is ethers. Let me go ahead and introduce that on this page. It's sort of written on the other handout as well. Ethers tend to be end products. They do not undergo a lot of different chemistry. The main reaction of ethers is cleaving them back to the alcohol and an alkyl halide. It's like the reverse of a Williams ether synthesis. I think I just want to move on to the. We can come back and see that and put it in context. Let's just start here. Cleaving them. It's called cleavage. It can also be called dealkylation. I'm not going to read that up there to you. Once we do it, you can look up there and see what we did, summarize it. Let's just do the chemistry. If you take this ether, methyl ether, react it with HBr, what type of chemistry can you propose? Let's address this solely based on mechanistic knowledge. What's the first step you might want to do here, mechanistically? We have an acid. What did I say when you have an acid? You're going to protonate something. One thing you can protonate is the oxygen. Okay? Now you got a Br minus. What can happen next?
You can leave the water, the oxygen.
This could leave.
Yeah.
If it left, would it leave from the carbon on the right, or would it leave from the carbon on the left?
Tertiary one.
Because you have two different carbons it's bonded to. We could either do SN1 or SN2. I'm going to tell you this is what the choices are. So let me ask you this. If we do SN2, tell me what happens. What would the bromine do?
Back to attack the carbon on the right.
Yeah.
SN2 is a nucleophile attacking, kicking off leaving group all the same. Which carbon are you going to do SN2 on?
Right.
Well, you don't do SN2 on tertiary carbon, so don't do it over there. But we can attack over here. I mean, that's a CH3. There's 3 H's there. It looks a little kind of like the end there. I mean, if we draw the CH3 out there, it looks more like more substantial. If we attack the carbon, kick the leaving group off of the carbon, bring the oxygen to leave, what do we get? We get the leaving group. That's actually the leaving group, right? So that's a big molecule. Plus what? Methyl bromide. And that could be an outcome. What have we done? We've cleaved the ether. We've dealkylated the oxygen. How many alkyl groups on the oxygen here? 2. How many now? Only 1 alkyl group on there. Cleavage of ethers gives what? Alcohol and alkyl halide. That is cleavage with HX, which is most common. Okay, what would the SN1 product be? What would happen SN1 back? SN1 involves making cation. Are you going to make cation on left or right? Left. So you make that cation plus, that's the leaving group in this mechanism. What can we do to finish it up and get this to a neutral product? Bromine now attacks, and we get this here. These being the 2 products. An alcohol and an alkyl halide. Alcohol and alkyl halide. So we have 2 options here, ways to cleave. Which one's going to occur here? Sometimes it can be difficult. You may get mixtures. I need to tell you what we're going to expect in this class and what I think is most common. And here it is. Whenever you have a tertiary reaction site present, always go SN1. Do we have a tertiary reaction site present?
Yes.
Yes. So what does the rule tell us to do? Go SN1. We don't get that. The top is our predicted outcome. If no tertiary site is present, do SN2. Now you got to keep in mind that sometimes you can a secondary carbocation may be just as stable as a tertiary, and so sometimes we may see a secondary, the rule not fitting, but I'll say, hey, but that's a super good secondary cation. So there will be exceptions to that. Okay, guys, let me set the stage for what you need to be doing with the day off on Monday. You need to do all of these. These are all cleavages. And also cleave cyclic ethers. We When you cleave a cyclic ether, it's not going to turn into two products. You're just going to open it up, it's still going to be one product. All these should be doable based on what we just did. That finishes up that handout, and we'll be moving on to oxide chemistry. Need to be doing some reading ahead to that. I'll see half of you in lab today. Have a good weekend, good break.